Welcome to lesson 2.1, identifying location in a distribution, percentiles, and z-scores. What is a percentile? A percentile describes the location in a distribution, kind of like quartiles do. It doesn't refer to the percent correct, so if Jenny scored a 91 on the test, doesn't mean that she's necessarily in the 91st percentile. She might be in the 98th percentile or the 81st percentile. Percentile describes the location in a distribution of a single point among all the points in the distribution. If Jenny is in the class of 25 students and makes an 86 on her test and is the fourth highest test score in her class, then is her percentile the same as her percent correct? The fourth highest out of 25 students means 21 students scored worse than her, and 21 out of 25 makes her at the 84th percentile. Jenny's at the 84th percentile but scored an 86% on her test. So the percentile means the percent of data values that are less than it. An alternate example, wins in a Major League Baseball. The stem plot below shows the number of wins for each of the 30 Major League Baseball teams in 2009. Calculate and interpret the percentiles for the Colorado Rockies, who had 92 wins, the New York Yankees, who had 103 wins, and the Cleveland Indians, who had 65 wins. The Rockies, because they had 92 wins, they had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. They had 24 teams score fewer wins that year. So they are in the 80th percentile because of 24 teams that scored fewer than 92 wins that year out of all 30 teams that were here. Okay? So since 24 out of the 30 teams won fewer games than the Rockies are at the 80th percentile. Okay, let's try the Yankees. The Yankees had 103 wins, which means that 29 out of the 30 teams had fewer wins than them, so they are at the 97th percentile, which is kind of interesting because we think normally that the team that did the best should be at the 100th percentile, but it's actually nearly, except for rounding, in large groups, it's nearly impossible to get that 100th percentile then by this definition, that the percentile is the count of how many teams or individuals had a lower value out of the total. Okay. All right. Then we would say that 29 of the teams had fewer wins than 103 wins in that year. So 29 out of 30 puts them in the 97th percentile. Since 29 out of 30 teams win fewer games, the Yankees are at the 97th percentile. The Indians, which was 65, okay, 65 wins is right here. Notice that there are two teams with 65. Not only because we don't know which is which, but because of this definition, to count all individuals with a lower value and then divide by the total, we would take neither of the 65s here, and we would only count the team with 64 wins, 62 wins, and 59 wins. And we would say that those are 3 out of the 30 teams. So since 2 teams won 65 games, the percentile looks for teams who won fewer games, count 3 of them, the 59, the 62, and the 64 wins. Okay, so 3 out of 30 puts them at the 10th percentile. Okay. Say at the 90th percentile, not in the 90th percentile. It's a small distinction. Percentiles are boundaries, so we can't be in a percentile. Percentiles should be whole numbers, so round your answer to the nearest integer. Here is a cumulative relative frequency, or ogive, graph showing the distribution of median household incomes for the 50 states and the District of Columbia. So what this means is that these are the cumulative relative frequencies. So they're pretty much like 20%, 40, 60, 80, 100% of states. And then the median household income. So almost 0% of states, or maybe 1% of states, has a median household income of $35,000. And then about 3% of states has a median household income of $40,000. And then over here at $45,000, or maybe just above 20, saying like 21 or 22% of states has a median household income of $45,000 or less. So California, with a median household income of $57,445, is at what percentile? So what we do is we go up from 57,000, which is pretty close to saying right in between 55 and 60, because it's just about 57,500. Okay, and then we go straight up to the line, and then we go straight across, and we say it's really, really close to the 80th percentile. So is it about the 79th percentile? That means that, interpret this value, that means that about 79% of U.S. states have a median household income less than $57,445. Okay? Remember, the word is less, not less than or equal to, because of the way that percentiles are calculated. We say that that percent of states has a median household income less than this. Another way of thinking it is 79% of states. Sorry, that was exactly the same way. Never mind. Okay, so let's move on. What is the 25th percentile for this distribution? What is another name for this value? This time, I'm talking about the 25th percentile, which is halfway between 20th and 30th percentile. So be sure that you're reading the axis correct. Right around 25th is right in the middle of this here. So 25th might be just above $45,000 for the median household income. The 25th percentile is approximately $45,500 median household income. The 25th percentile is also the Q1. Make a relative, meaning in percent, frequency histogram for this data. Remember, histograms work totally differently. Histograms are talking about what percent of states are within each of these here. So from 35 to 40 median household income, we found that there's only about 3% of states that are in that interval. And then from 40 to 45, we found that somewhere between 3% and about 22% or so. So 22 minus 3 is about 19-ish percent. So then we go right below 20% for that next bar. And then from 45 to 50, we went from about 21-ish, 22-ish percent to about 50-ish percent. So that would be about 27-ish percent. And so then we put 27% of states are in that interval. And let me just keep going. That was pretty steep, right? I would picture this as a little bit less steep. And sure enough, that means that from 50 to 55 median household income, which is where those dots are, that there was just a little bit fewer states than there were in this steep section. Now I'm going slowly through this because it's important that we can interpret what these steepnesses mean. So a less steep means that there's fewer states in that interval. More steep means that there's more states in that interval because it's a greater percentage of states in the interval. So to go from 45 to 50, we have a steeper climb. Okay, so a little bit less steep here. I'm going from just about 50% to just about 78-ish percent. So that's only about 18-ish percent. Let's see if I got that right. 50. Oh yeah, just about 28-ish percent. Okay, so there we are. And then the next group is from 55 to 60, and that goes from about 78-ish to about 80-ish, maybe more. So before I calculated that it was about 10%. Now looking at it, I think I'd call it more like 5% or so. Okay, because it looks like it goes from just below 80 to just about 80, but maybe I saw it as going from about 70 to about 80 before, so I gave it a 10%. Okay, kind of tricky to tell these things, especially as I get further away from this axis. So I'm going from just above 80 to just about 90 this time, so I might maybe a little bit more steep, so I might just go right above 10%. And then for the last one, I'm just going from about just above 90 to just about 99, so maybe like 8-ish, okay, percent of states. So 8-ish percent of states are between 65 and 70,000 for median household income. And obviously, if I took all these percents, if I did a good job of estimating from here, all these percents should all add up to 100%. Okay, where is the original graph the steepest? What does this indicate about the distribution? I would say steepest was right here, and I would say that means that most of the states in America have a median household income of between $45,000 and $50,000. So it is steepest between $45,000 and $50,000. This indicates that between $45,000 and $50,000 is the largest percent of states having median household incomes versus the other median incomes. How do you determine shape from a cumulative relative frequency graph? Well, symmetric, we would see the steepest part kind of balanced among two equal length, less steep areas. So the tails are of equal length. It's steepest in the center. Right skewed would mean that there's only a little bit of small climb. And so that indicates that there's just a small percentage of individuals in this first amount of X value, but then in the next amount of X value, shortly after that, there's a large amount of people, meaning that we go from like maybe 5% to like 95%. So we would maybe say like 90% of individuals are over here on this X-axis, right in here. Okay, and that's still fairly close to the left. Then I see very few, meaning it only goes from like 95 to like 100%, okay? Very few individuals in that whole other section. So that would mean that I had about 95% of my individuals in the first third of my x-axis, and then the rest of the x-axis had the whole other 5% of individuals. So I would say that that's skewed right because of the vast majority on the far left, and then very, very few, but still some reaching all the way out to the right. And skewed left is just the opposite, a very, very small, very, very long tail, very, very small climb, okay? And then a very steep climb, short tail, okay? So then I would say that's skewed left. Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller relatively speaking? That is, relative to other kids of the same age, who is taller? According to the Centers for Disease Control, the CDC, and Prevention, the heights of 3-year-old females have a mean of 94.5 centimeters and a standard deviation of 4. The mean height for 12-year-old males is 149 centimeters with a standard deviation of 8. Okay, so what we're talking about is she was 100 centimeters tall, and the mean for females is 94. So she's about 5.5 centimeters taller than the mean. He is 158 centimeters tall, and that is about 9 centimeters, that is 9 centimeters taller than the mean. So she was 5.5 centimeters taller than the mean. He is 9 centimeters taller than the mean. But look at the difference in means. Girls at this age are quite a bit shorter than boys. They're about 2/3 the height of boys. So they should vary a little bit less than the boys should vary, just because there's less there of them. Okay? So if they all varied by about 10% from the average, on average, then we would, 10% of this value on average, and 10% of that value on average, then we would typically see more variety here, about 15 centimeter variety on average, and only about 9.5 centimeter variety on average. But we have that exact actual data. We see that girls vary by about 4 centimeters on average from the mean, and boys vary by 8 centimeters on average by the mean. So the variance is even greater. It's only, it's double the variance for the males. So was her 5.5 really greater, or was his 9 really greater now that we see these standard deviations? Macy is 5.5 centimeters above the mean, and the standard deviation is 4 centimeters, so that 5.5 centimeters means she's greater than 1 standard deviation. In fact, she's 1.5 centimeters greater than 1 standard deviation above the mean. Brady, though, is 9 centimeters above the mean, but the standard deviation is 8 centimeters, so he's also more than 1 standard deviation above the mean, but he's 1 centimeter more than 1 standard deviation above the mean. Okay, and the standard deviations are double for the men. Okay, so what I'm talking about is taking Macy's height and subtracting from the mean to get that 5.5 centimeters above average, and Brady's height and subtracting from the mean and getting that 9 centimeters above the average. Therefore, we see Brady is taller than the average boy by a greater amount, okay? Because he's 9 centimeters above the mean and she's only 5. But look, he's a 12-year-old and she's a 3-year-old. So there is more variety in height among 12-year-olds than there is among 3-year-olds, okay? So therefore, Brady is taller than the average boy by a greater amount than Macy is taller by the average girl, because 9 is bigger than 5.5. But let's equate for their age in a way I'm equating for their variety of heights at those ages. So take that 5.5 centimeters above the average and divide it by 4 and get how many standard deviations she is above the average. She's not just greater than 1 standard deviation above the average. She's not just greater than 1 standard deviation plus 1.5 centimeters. Okay, that's kind of odd to mix the units of standard deviations and centimeters. Let's just change it all to standard deviations. When we divide by standard deviations, we're talking about how many centimeters she is how many standard deviations she is above the average. So she's 1.375 standard deviations above the average. He is 1.125 standard deviations above the average. They're both greater than 1 standard deviation above, but she has a greater number of standard deviations above the average than he does. So Macy is taller for her age. Is being 10 above average a big deal? It depends on the context. In height in inches, yes, being 10 inches above average is a big deal. In salary in dollars, no, making 10 more than the average is negligible. So really, that value above the average is alone not enough to compare. We need to also compare by the standard deviation and see how many standard deviation units we are above the mean, because that accounts for the amount of variability. There's a lot less variability in inches in height than there is in dollars in salary, because inches in height tends to be around 50, 60, 70 in those units, but dollars in salary tends to be around thousands of dollars and tens and hundreds and millions of dollars. Okay, so are the data values that go into salary. Okay, let's read the next one. Tri-mean, this is not really important for AP stats, but it's here, so I just thought I would describe it to you. Tri-mean means a trimmed mean. To calculate the trimmed mean, Minitab removes the smallest 5% of values and the largest 5% of values and calculates the mean of the middle 90%. This makes the trimmed mean more resistant to outliers than the regular mean. This trimmed mean method is used in some sporting events where subjective judging exists, such as in diving and in gymnastics. Also, standard error of the mean is the standard error of the mean, which is equal to the sample standard deviation divided by the square root of the sample size. We'll learn much more about the standard error of the mean and how to use it in chapters 7 through 10. Standard error of the mean does not actually account for the, it's kind of like a guess of the standard deviation, so don't use it for now. Okay, how do you calculate and interpret the standardized score, or z-score? Do z-scores have units? What does the sign of a standardized score tell you? The z-score tells us how many standard deviations away from the mean an observation falls in the direction above or below. So positive values, an observation is above the mean, and for negative standardized values, the observation is below the mean. To calculate, we use this formula, z equals xi minus x bar all over sx. So it's observation minus the mean over the standard deviation. Okay, or in population notation, z equals xi minus mu over sigma. We did this up above. We took Macy's unique height, okay, she's an individual, so xi, minus the mean, x bar, or mu, because it looks like it's the mean of all 10-year-old females. Okay, and then we divided by the standard deviation of 4. For Brady, we took his height, 158, divided by the mean, subtracted from the mean, divided by the standard deviation. Observation minus the mean divided by standard deviation. And then these two values here we'd call their standardized scores. Z equals 1.375, Z equals 1.125, saying that she is 1.375 standard deviations above the mean, and he is 1.125 standard deviations above the mean. Home run kings. The single-season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 61, Mark McGwire hit 70 in 98, and Barry Bonds hit 73 in 01. In absolute sense, Barry Bonds had the best performance of these 4 players because he hit the most home runs in a single season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than in others. This is due to many factors, including quality of batters, quality of pitchers, hardness of the ball, dimensions of the ballparks, and possible use of performance-enhancing drugs. To make a fair comparison, we should see how these performances rate relative to other hitters of the same year. So we're kind of norming them to their year. We're finding how good they are relative to the time. So let's see how much they stand out. Calculate the standardized score for each player and compare. As we realize, we're not just curious how far away they are from a mean. We're curious about that relative to how much variety there is of the players at that time. Okay, so we need both aspects here, the mean and the standard deviation. So we take each player, Babe Ruth, take his number of home runs minus the mean and divide by the standard deviation because we want to figure out how many units he is actually above the mean according to the variety of players there were at that time. Okay, so all players, let me go over that again. I'll just show you the example for Maris. Observation minus the mean, take that and divide by standard deviation. Mark McGwire, observation minus the mean over standard deviation. They're all pretty much lined up for you, just the data you need. Bonds, observation minus the mean divided by standard deviation. All players are more than 3 standard deviations above the mean, 5, 3, 3, 3. However, Babe Ruth is the home run champion relative to each batter's year and others in the league. In 2001, the Arizona Diamondback, Mark Gracie's home run total had a standardized score of negative 0.48. Interpret this value and calculate the number of home runs he hit. So what we mean here is I'm going to take the observation minus the mean over the standard deviation, and here I corrected myself and changed it for population notation because I am talking about the data of all the players at that year. So I'm going to take negative 0.48, and since he was in 2001, I have the data for the mean and the standard deviation in 2001. So I'm going to subtract it from 21.4, divide by 13.2, and then I know though what his z-score is. His z-score was negative 0.48. So I'm going to start with z equals negative 0.48. I don't know actually how many home runs he hit, because it's a hypothetical situation that you would know a z-score for someone. Subtract from mean, divide by standard deviation. So first thing I'm going to do is I'm going to multiply the 13.2 to both sides, just because I'm jumping back to Algebra 2 land, where I'm looking for a variable over here in the numerator. So I need to get rid of this denominator, because it's a grouping symbol right here, serving its place right here as a division bar. So I need to get rid of the grouping so that I can enter the grouping and start to get rid of things right in the grouping. So times by 13.2 to both sides, add 21.4 to the other side, and I get 15.064. Grace, whose home run total was 0.48 standard deviations less than the mean, totaled 15 home runs. Okay, so because he was 0.48 standard deviations less than the mean, we had a negative z-value. So you have positive z-values and negative z-values, and that just means that if there's a mean somewhere, okay, then there are standard deviations above the mean and below the mean, okay? Because the mean is the middle. And if we talk about either notation you want to use there, I guess I'm using population notation. So if we talk about a standard deviation above or below the mean, then we're saying that somebody is 1 standard deviation or 2 or 3 standard deviations above the mean, or 1 or 2 or 3 below the mean. And I know we're all hyper competitive out there, so we all want to be above the mean, but in many ways I'm sure that we're below the mean. Maybe your hair length is shorter than average. Maybe your nail length is shorter than average. Maybe your toenail length hasn't been cut in a while. Your toenails haven't been cut in a while and they're longer than average. Okay, so all parts of life is above and below average. Okay, I think we're good there. Thank you for joining. Have a great day.